Good morning, afternoon, or evening. Let us imagine we are walking into a bar. A wave of wonder hits us, and we ask ourselves, what is the probability that two people in this bar share a birthday? Just as we pose this question to ourselves, another person walks in. Another question arises. What if more people came in and had a drink? How would this probability change? With a stroke of genius, we reach for a very abstract other possibility. What if I could even change the length of a year? What effect would that have? Now, the terminology becomes less applicable, so we try to formalize our question. What is the chance of collision when randomly sampling Q samples from n options? Ergo, P of Q, n. This question is titled the birthday problem. To consider this question, we will be simulating it with random samples. Let me introduce you to our calendar. Each dot you see is a day. This calendar does not have any month separations because we determined the amount of days was variable. At its current state, this calendar does not do much. This is where we start playing with color. For each day, and thus each dot, we need to indicate how many people are born on this day. We use gray for days without birthdays, dull and bland days. Then, when we have a single birthday, we use a dark red color to indicate this. When we have two birthdays, this red color becomes vibrant. For more than two birthdays, the vibrant red color becomes a little brighter, and for days with 4 or more birthdays, the same color is used. Now is probably a good time to mention you can go to javernus.com/birthday and play with an interactive version of the visualizations you see in this video. Let us get started populating this calendar with birthdays. We look through the room and count 23 people, including ourselves. So we decide to draw 23 numbers, randomly sampled from 1 to 365. Sadly, no dice. We recall we are dealing with randomly sampled numbers and probability, so we realize we should average over many runs. We decide to program this. We create our control panel. We plan for the future and build in everything we may need. A selector for the amount of days, a selector for the amount of people, a reset button which might become necessary at some point, an update button for redrawing the birthdays, and a super update button for redrawing birthdays 100 times. With this, we armed ourselves with all the things we need to tackle this problem. Time to put them into action. We use our system and reroll many times over, but find ourselves forgetting whether we counted 6 or 7 collisions of birthdays. Furthermore, we are only rolling 23 birthdays. Doing it all by hand became tedious, so we put this information into a graph and automated much of the data collection. We now sample from one person all the way up to 50 people and plot the results in the graph. Each possibility for Q, ergo the amount of people, is run 100 times to compute an average of the probability. This average looks very scattered, however. Each time we update the plot, another 100 runs is added and averaged. After a handful of updates, the dots begin to form a line, a function. When we use our super update button, we essentially click update 100 times, speeding up this process. If we now have a look at the value we are getting at Q is 23, we see the probability is around 50%, hovering just under 52. We can now introduce two functions for the upper and lower bound of this probability. Y is Q times Q minus 1 over 2n, and Y is 0.632 times q minus 1 over 2n. These bounds should encapsulate the lower region where q, the amount of people, is small. With these bounds, we can now experiment with different amount of days in a year by varying n. When we vary n, we notice that the bounds move as well. The larger n is, the lower these bounds become. By trying out different options for n, such as 170, 365, and 500, we can experimentally prove that they hold for all these options. The bounds hold for any arbitrary n, so long as q is small relative to n. We notice that the upper bound always holds, while the lower bound cuts into the dotted function line at some point. This point seems to always be above the 50% line. In applications in cryptography, where the birthday problem is usually taught, the lower bound being applicable up to 50% chance is more than adequate. In cryptography, one usually finds values for n from 2 to the power of 128 upwards. For any sampling that can be done in these cases, q would not nearly reach n at all. Thus, the lower bound satisfies requirements for cryptographers. To summarize, we've gone from a wandering of our mind to experimenting by hand to writing a program to tell us some fascinating information about probabilities that might seem counterintuitive at first. We validated lower and upper bounds for the probabilities we got, and even glimpsed at a use case for the specific problem. Lastly, I want to refer you once more to javernus.com/birthday to check out the visualizations for yourself and play with it a bit to build up a new intuition. Thank you for sticking around. As your host, I wish you a wonderful day.